Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to talk about some different properties of definite integrals and how it may affect the way you evaluate them. And then we are just going to get some practice applying these properties to some problems. So take a look at these 8 properties right here. And before I discuss any of them, see if you can go through and maybe take a good educated guess of what they would be equal to. Some of them you may not know what you're expected to write, but for some of them you may be able to give what you think is the correct answer. So pause the video, see if you can figure any of them out, and then we will discuss. Okay, so if I look at number 1, and that is, let me make this a little bit bigger. So number 1 says the integral from a to a of f of x dx. What should that be equal to? Well, if I look at this visually, right, maybe think about this algebraically and you already can know what the answer is. But if I think about this visually, well, if I have a graph and here's a, if I have a function, well, the area from a to a, there would be no area, right? Because the width of that geometric shape would be 0. Right? There would be a height to whatever the function goes up to, but the width would be 0. So there would be no area, which means the answer to this integral would be 0. Now, that's visually. If I think about this algebraically, using the fundamental theorem of calculus, I would get the antiderivative of a, antiderivative evaluated at a, minus the antiderivative evaluated at a. Well, anything minus itself is going to be 0. So algebraically, it makes sense why it's 0. Visually, hopefully, it makes sense why it's 0. But the answer to any integral going from the same starting point to the same ending point, that answer is going to be 0. Let's take a look at the second one. Here, we are told that there's a number in between the limits of integration. So we have an interval a to b, and we know that there's some c value in between. Well, let's do a visual example first. So let's say here's a, here's b, and there's going to be some c value in here. We don't know exactly where it is, we just know it's between a and b. Well, if here's my function, right, the first way I could find out the area is just find the entire area from a to b, right? And that would be the answer to my definite integral. But I could also break this integral up. All right, so I could break it up at c, find this area, and add them together. And those are both going to be the same as if I just found the entire area. And you may say, well, why would I need to break this up if I could just do the whole thing? Well, sometimes it'll be much easier to evaluate the entire integral in pieces than it would be to evaluate the whole thing in one shot. So if I wanted to break this up, I would do the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And that would be equivalent to the entire integral. If I'm moving on to the next one, so if I have an integral that is equal to a certain value, right? So they're saying this integral is equal to k. Well, if I switch the limits of integration, okay, so instead of doing, let me write this out for us actually. Here, right, this would be equal to f of b minus f of a. Well, if I switch those and do f of a minus f of b, think about what happens when you have a difference and you just reverse the numbers. So, if I have 5 minus 3, right? That's equal to 2. What happens when you switch the two numbers you're subtracting? So 3 minus 5. That's going to give you negative 2. And that would be true of whatever numbers you have, even if they're negative to start with. So if I had negative 2, minus negative 5, well, that's going to give me positive 3. If I do negative 5 minus negative 2, that's going to give me negative 3. So if all you do is switch the limits of integration, it doesn't change the area, it just changes the sign. So this would be equal to negative k. Again, just when you switch the limits of integration, you're going to get the opposite area of what you would get if you had them set the other way. A lot of times, you'll see this, right? Most of the time our limits of integration are going from left to right, right? So you're going to have like the limits of integration being, 0 to 5 of f of x dx. So if you knew what that area was, you could pretty easily figure out the area going from 5 to 0 because you would just put a negative sign in front of that area. Okay, moving on to the next one. And this one's very similar to number 3, right? If I switch the limits of integration, so they're saying essentially if b is less than a. So if you had a function and you put b before a, so our function looked like this, and you wanted to find that area, well, normally they're going to write it with the smallest value or the most negative value at the bottom of the limits of integration, right? So if you wanted to write it that way, you could switch those and have it go from b to a of f of x dx. It's just going to change the sign, right? So your answer is going to be negative. Or it's going to have a negative sign in front of it. Maybe if your original answer is negative and then you put the negative there, it turns positive, but it's just going to be the opposite sign of what you found originally. So maybe it's easier for you to evaluate it going from B to A rather than A to B. That's fine. Do it that way. Just know that you just need to put a negative sign in front of your answer at the very end. Hopefully we see the relationship, though, between number 3 and number 4 here. All right, let's talk about number 5, and let's clear some of this up, actually. Number 5, if k is a constant and you're taking a definite integral, you can just pop the k right outside, right? Just like we did for derivatives, I can rewrite this as k times the integral a to b of f of x dx. Sometimes it's easier to pop it out. Sometimes it's easier to keep it in. Just know that you can do either. Number 6, a sum or a difference. Just like derivatives, you can break these up. So sometimes it's easier to add the functions together first and then take the integral. Sometimes it's easier to take the integral of each function separately. So this could be equal to the integral a to b of f of x dx, plus or minus, depending on what you have, the integral from a to b of g of x dx. So you can break it up if you want. You can leave them together, whatever turns out to be the easiest for you. Let's go look at 7 and 8. These two are less important. You're going to run into them, I'd say, far more infrequently than you do the other limit properties. However, there could be a question that pops up there in the AP exam, and you may have to know, what these properties say to be able to figure it out. So the first one deals with an even function. And an even function is one that just has symmetry with regards to the y-axis, right? So if you think about the y-axis, the function is symmetrical around that. Well, what that means is if you take a number on the left side and the same number, so we'll actually make this negative a, and the same number on the right side, You could actually just take half of that integral, right? Either the half on the left-hand side of the y-axis or the side on the right-hand side of the y-axis, and then just multiply it by 2. So two ways we could do this. This is equal to 2 times the integral from 0 to a of f of x dx, or that's equal to 2 times the integral from negative a to 0 of f of x dx. And again, because it's symmetrical around the y-axis, there's going to be the same amount of area on the left-hand side as there is the right-hand side. So again, you could just find half of the integral and multiply it by 2 if you wanted to. For an odd function, it's a little bit different. An odd function is symmetrical about the origin, which means that, and again, it depends how it's drawn, right? Because you could have an odd function that looks like this as well, right? That's also symmetrical about the origin. But you'll notice for either the black or the purple, there's the same amount of area on both sides of the y-axis, except one will be above, right? So let's say I'm using the purple, and I go from negative a to a. So there's the same amount of area, but one of those areas is above, and one of those areas is below. So if it's the same amount of area, but one's below, one's above, that means the answer to this integral is going to be equal to 0, right? Because you're going to have a positive value and a negative value that have the same absolute value. So those are the integral properties we're going to look at today, and now we're going to apply them to a variety of different questions. And I think we're just going to do 1 and 2 together. So the top 2 questions, and then you can practice the other ones on your own or during class, and then we'll take a quick look at the last page before we're done. So here, we're not actually going to have to take any antiderivatives because it tells us what the answers to these 2 integrals are. We're just going to have to use limit properties to figure out, these new integrals that are written. So the first one, and again, pause the video and maybe try to figure out numbers 1 and 2. And then come back here and listen to the discussion. So for the first one, you'll notice all they've done is switch the limits of integration. So if we think back to one of the properties up above, this is going to be equal to the negative value going from 0 to 3 of f of x dx. We know that this value right here, that's equal to 6, right? So our answer to the integral that they give us here is just going to be negative 6. So it's just the opposite sign of whatever that original integral was, or the given one. For number 2, we actually have to do a sum here, right? Because this is the one where we have a c value in between the 2 limits of integration. So we could break this up and go from 0 to 3, with 3 being our c value of f of x dx, plus the integral from 3 to 7 of f of x dx. And remember I said there would be some circumstances where it's much easier to evaluate the entire integral. Much easier to evaluate the integral in pieces rather than trying to do it all together. Well, if you tried to do this all together, you wouldn't be able to do it, right? Because we don't have an answer for the entire integral. We just have an answer for the 2 pieces. So we'd actually have to add the 2 pieces together to get our answer for the whole. So this is going to be equal to 6 plus negative 8, which gives us negative 2. Okay, feel free to try the other ones on your own. We'll also have some time to work on those during class. Let's jump down to the last page, though. A little bit different. Here they give you a visual example of f of x, and then they ask you a bunch of different questions. So you're going to have to think about maybe finding areas using different area formulas, for circles or trapezoids, rectangles, triangles, etc. Let's just do the first one. Again, you will use some limit properties here, but we'll just do number 1 for time's sake. So it says find the value of the integral 0 to 3, or find the value of the integral where the limits of integration are 0 to 3 and the function is f of x. And again, this function right here is f of x. Well, we know that this just represents the area between the function and the x-axis from 0 to 3. So it's this entire area right here, which isn't very easy to find if I'm trying to do that in one shot. So I'm going to break this up into several different, actually we can just do two. Right? If you don't remember the area formula for a trapezoid, you may have to break it up into a rectangle and a triangle, but most efficient would just be the quarter circle and the trapezoid. So area of the quarter circle would be 1/4 pi r squared. Our radius here being 2. So it's going to give us, oops, forgot the squared there for a second. That's going to give us 1/4 times 4, which is 1, so we are just left with pi. Area of the trapezoid, that's equal to 1/2 times the sum of the bases, bases being the horizontal segments. So my bases are 2 and 3, and my height of the trapezoid is 1. So this ends up just giving me 5/2, or 2.5. So area of this right here, of this integral, 0 to 3, of f of x dx, we could use no calculator here, so we'll just keep it as pi plus 5/2, or pi plus 2.5. All right, I was going to cut the video off here, but I would like to go over one of the two at the bottom, just because they're significantly different than these other three. So let's take a quick look at what those say. We have to make this a bit smaller, though. And I may not be able to, yeah, we'll just leave it like that. So it says, if f of 0 is equal to 5, what is the value of f of 3? And again, when they're using the uppercase f, they're just talking about the antiderivative. Because we know that this function represents f of x, so you could think about that as the derivative, and capital F of x being the original function. So if we know what the antiderivative of 0 is, we need to figure out the antiderivative of 3. Can we set up an equation here? So think about, can you set up an equation using the fundamental theorem of calculus? Let me just put that up here, although hopefully we know what that is right by this time. So the integral from a to b of f of x dx, as long as that function is continuous on that interval, we can figure that out by taking the antiderivative of b minus the antiderivative of a. So can you use this equation here to come up with just one unknown down here? So pause the video, see if you can do that. If you are, then think about how you could solve it. And then we'll quickly discuss before we end this video. Okay, so the answer is we can, right? We can use the FTC to set up an equation here. My interval is going to be from 0 to 3. And the clue here, right, is that they are talking about evaluating the antiderivative at 0 and 3. So the interval from 0 to 3 of f of x dx should be equal to f of 3 minus f of 0. Now, can we fill in enough here? We need to figure out f of 3. So this right here should be our only unknown. So can we figure out the values of the left-hand side of that equation as well as capital F of 0? Well, we could just use what we did for the very first question to figure out this portion, right? we did that for the one up top. We found that that area was pi plus 5/2. And if it wasn't something we had already figured out, we could just come up here to the diagram of f of x and use area formulas to figure that out. I don't know what f of 3 is, but I know that f of 0 is 5. Well, I've got one unknown here, and the only thing I need to do is add 5 to both sides. That is going to give me pi plus 15/2, or 7.5, is equal to f of 3. And there is your answer. So you may have to do something similar with the very last question on this page. Try to set up an equation using the FGC part 1. All right, now we are going to end the video. As always, enjoy the rest of your day, and we will look forward to seeing you for our next lesson.